I love being a software engineer because of how easy it is to build side projects. And I've built countless side projects. I've built a social gambling application, a dating website backend that had 0 users, a stock trading music rhythm application for Android. And I think every developer should have side projects. So when I have a web app that I want to deploy and share, I want to show my friends my most recent project that nobody will care about, I use DigitalOcean to quickly spin up a server and host my projects. And who knows, if one day one of my apps takes off and goes viral and people actually do care, I can easily scale using DigitalOcean's flexible pricing plan. Companies like TaskRabbit that have grown rapidly have used DigitalOcean for this very reason. But until this happens, I will happily stick with the $5 a month plan. Sign up with promo code SEDaily to get a free $10 credit as a listener of our show and start building your apps. We would love to see what listeners build, so send us an email showing us your project. I've also interviewed Moise Uretsky, who is the co-founder of DigitalOcean, and he mentioned that the ease of use and the flexibility is why they built the service in the first place. That DigitalOcean interview is one of my favorite episodes. Moise talks about bleeding in a data center. He says, you don't know how hard it is to do a cloud hosting service until you've bled in a data center. It's really interesting. So speaking of which, let's get on with this episode of Software Engineering Daily. Riak is a distributed NoSQL key-value data store. Jon Meredith is the chief architect at Basho, which makes the Riak data store. Jon, welcome to Software Engineering Daily.
Thank you very much for having me. It should be a lot of fun.
Riak is an implementation of the Amazon Dynamo paper. So let's start by talking about that paper. To get some historical context on that paper, what did the landscape of distributed databases look like in 2007 when the paper was published?
So I would say most people were working on relational database management systems. MySQL, Postgres have become quite popular in small shops. Larger enterprises had things like Oracle DB2 running their workloads. There were a few sort of interesting distributed systems that were bigger than just master-slave replicated relational systems like maybe Vertica, and I know certainly that MySQL had its own clustered version of it that ran on top of its own network database. But as a whole, people were very much in a relational structured world.
So why was the Dynamo paper so significant?
So I would say partly as a result of its timing. At that time, internet businesses were definitely here to stay. People had been connecting them to the internet, connecting their internal systems to the internet via web apps, and feeling a lot of the pains of running high availability systems. And I think a combination of that and the fact that the paper was just so accessible, laying out sort of problems that Amazon had and putting it in terms that were not, overly academic, and that they do describe each of the techniques, but not overly heavily, but at a level that I would say a sort of practicing programmer with some experience would feel comfortable taking a crack at it. And indeed, that's exactly what quite a lot of hobbyists and small organizations did do, all the way through LinkedIn.
Yeah, it is a very readable white paper, and we'll link to it in the show notes. What are the unique problems that Amazon was running into? Or maybe they weren't completely unique to Amazon, but maybe they were being encountered by Amazon and other giant scale companies in 2007.
Yeah, the use case they describe in the paper is their shopping cart system. They basically want to be able to always record customers' intentions and not slow them up in doing it. I remember at the time they published some stats on just how much latencies cost them. So they said, I think around 2008, that a 100 millisecond increase in latency cost them 1% on their top line on sales, something like that. So obviously they're very keen on making sure that their systems were resilient and robust and continue to operate 24/7, which was something that a lot of people were just starting to get used to.
So this idea of the shopping cart as the prototypical use case, you always need to be able to write to the database entry the database entity that is the shopping cart. And this always writability, this high availability for writes is actually important in a lot of places across Amazon. Why is the high availability of writes so important?
Well, I think it's because if you aren't able to take the write consistently, if you were to say, hey, I have to keep my shopping cart absolutely up to date, then if something goes wrong and you can't handle that, you have to say to the user, I can't do anything about it. Whereas if you store perhaps the piece of information that you added, you store the fact that you're adding one particular item to the shopping cart and you can write that somewhere, the chance that the user's immediately going to need to know what was in the whole shopping cart isn't necessarily there. They may continue shopping, and it may only be at the point where they actually check out that they have to, they'll go through and they'll do a quality check themselves and saying, look, here's my list of things that you said you ordered, please check it, and then press proceed. So you're able to give them effectively a much nicer user experience while dealing with a lot of load.
Talking more broadly, what are the major components of a Dynamo-style database?
So the big pieces, I suppose, are a gossip dissemination system to share data around the cluster without having a particular master node. It uses consistent hashing to work out where to distribute the data across its nodes. A quorum replication style system to make sure there are multiple copies so that we don't have single failures, and version vectors to make sure that we can track the history of objects in the system, as well as some anti-entropy mechanisms that I think are another very interesting part of resilient systems. Okay,
great. And we'll go into some of those discussions, but let's contrast the Dynamo style database that we haven't discussed in detail much yet with the more classical type of ACID compliant database. Why does the ACID compliance lead to poor availability?
So first off, let's just remind ourselves that modern relational databases are marvels of modern software engineering. The things that they can do are truly incredible. They can take queries that anyone wrote and run them relatively efficiently in lots of cases. But when you start trying to spread that sort of spread the data across more than one machine to get the resilience that you really need for high availability, you start to have some problems which they're able to solve, some problems with consistency that they're able to solve locally because they're on a symmetric multiprocessor box. They have relatively fast paths between cores and memory and those sorts of things. And that problem then shifts to either replicas being even on multiple machines in the same data center or possibly even on continents. And that makes it so that if you're not able to reliably update a sufficient number of them, depending on what your system is for keeping everything consistent, you become unable to update things, and that is indeed the sort of crux of the problem that we're dealing with here. So, but even symmetric multiprocessor boxes, they start to even relax some of the ACID guarantees, even on a local box for performance reasons. There's some very interesting work that Peter Bayliss did a couple of years ago that's detailed on his blog about how ACID really is your ACID database, and things like using MVCC and some of the other ways of reducing some of the isolation levels that they've got makes it so that they don't quite act as ACID as you may think they do.
So still talking at kind of a high level, describe how Dynamo trades off the high availability, like we talked about the high availability of writes with the shopping cart. How is that trade-off of high availability kind of maybe not mutually exclusive, but how does that compare with a highly consistent database? And how does high availability trade off with consistency?
Well, so the Dynamo system takes an eventually consistent approach to things. Instead of expecting you to be able to immediately see an update, it just promises that once all updates stop happening, it will eventually propagate copies to all of the right places, and then you will eventually see it. So that gives a lot more latitude on how it can synchronize and repair itself. But as a programmer, you may be slightly surprised to see some of the ways that manifests, like, for example, writing something and then reading it back from possibly a different replica in the cluster and getting either an older value or a not found value, depending on how you've tuned your quorum. But as the mechanisms kick in to distribute data or repair data, then you will eventually get the values that you need, probably by the time that you need to check out.
To give the listeners some further motivation to paying attention to the higher granularity that we'll go into, what are some of the other what are some of the databases that were inspired by the Dynamo paper? Like how give me an idea of the gravity of this paper.
So you can trace out a large number of routes of them. Immediately after the paper was produced, Voldemort came out very early from LinkedIn. I know people like Cliff Moon wrote Dynamite, which is something come and gone. There's all sorts of fun implementations of it that you can see over there. There's an old Erlang one called Kai that does it. But as far as sort of bigger mainline systems, Riak is obviously highly influenced by it. Cassandra by Dynamo in the Big Table paper. If you look on the Wikipedia entry, it'll say things like Aerospy Car. But I would say a huge number of systems have been influenced. Around some of the operational concerns that they were going for in the paper, as much as the architecture.
Okay, great. And I want to get into some of the distributed systems concepts that Dynamo implements. And I want to start by saying that I think one thing that's interesting about Dynamo is that it didn't necessarily make fundamental breakthroughs as much as it surveyed the landscape of different distributed concepts that were going on and found out which ones to fit together to mash up to get the right mix of properties that they wanted. Would you say that's accurate?
Oh, absolutely, and it says as much in the paper itself, and that the authors are quite self-effacing about it. What's so nice is that for people who aren't perhaps experts in distributed systems, I personally came from a more database background. Seeing all of the, seeing perhaps an opinionated grab bag of techniques to say, hey, I'm going to use Merkle trees for my anti-entropy synchronization. I'm going to use version vectors to track causality. I'm going to use consistent hashing to distribute data. Specifically, this style of it is incredibly valuable. That they make no claims that their main contribution is really showing how the system can be built, showing how it can operate at scale, and they publish information in the paper about how often they actually hit siblings in their data, how their high quantile latencies looked over high load periods, and techniques that they had to use to try and reduce some of those effects.
And to ease into the conversation of distributed databases, how many times, so a single piece of data, for example, like a user's shopping cart, how many times is that piece of data replicated across a typical cluster of Dynamo-style databases?
So we use a quorum style of coordination normally. So typically the number that makes sense to start with is about 3, and I would say the vast majority of data stored in them is probably around that. There are different ways that you can use it. If, for example, you had a catalog system where you wanted to scale your read throughput, you could store many more replicas and have more available to read back. But it's obviously much more expensive to update things, and it takes more space to store them. But 3 would probably be the magic number.
So for some listeners who are unsure of what the term quorum means, or they're unsure of this, they don't know much about distributed consensus. Why is the number 3 important in order to get this quorum, and what is the term quorum?
So a quorum of nodes is basically an agreement. So you have, if you have 3 nodes, then you need to make sure you get 2 responses back so that you can have had enough 2 out of 3 of any of the most recent updates that you've had. So if you just wait for 1 response, if you only write, say, two replicas out of 3, and then you read back, if you read a different 2 out of 3, you're likely to get, you will get one of the 2 that you originally wrote.
Okay, great. So we'll walk through the anatomy of a write and a read if that is not clear yet eventually. But let's talk about some more of the properties. So Dynamo is symmetrical, which means that every machine operates in the same way. And this is in contrast to a master-slave architecture. How does a master-slave architecture contrast with a symmetrical architecture?
So the way that I think it's probably easiest to think about it is responsibilities. If the master is effectively responsible for making all of the decisions, and the slaves would just record and apply them, and typically with a relational system, that's done via log shipping. The master records all of the changes it makes to itself. It sends them on to the slave repays them. Whereas in a Dynamo system, each of the nodes can be actors in the areas that they have joint responsibility for, which we'll probably get onto later and talk about vector clocks for tracking that. But instead of having to reconfigure the system when a master fails, either dynamically or administratively, the Dynamo system is able to take care of that itself, because there was originally nobody in charge anyway. So it's it sidesteps the whole issue of who is the master, who's in charge.
Are there any other shortcomings of a master-slave architecture?
The primary one for me is that you have to deal with very complicated sharding arrangements to deal with write throughput. All of the writes must go through that one serialization point of the master. And so, although it's very easy to add slaves or tiers of slaves as data fans out, for write-heavy workloads, that makes it a lot more difficult to handle.
Right. So Dynamo is also heterogeneous. In a heterogeneous or heterogeneous system, the operators should be able to replace the system's old hardware with new hardware. And the system should be able to leverage additional capacity from the new hardware. What are the challenges to having a system that can implement heterogeneity?
So the way that the Dynamo paper suggests handling that is by effectively giving each node in the system a weighting of how much responsibility it takes, and that's sort of applied through the consistent hashing system. The harder parts to it are that the database systems are really a combination both of storage and IOPS, the number of IO operations they can perform per second. And they don't necessarily scale linearly. If you buy a new hard disk, it may be double the capacity, but it may only be 10-20% more IOPS than you would have had before. So there are some very interesting challenges there, working out, when people think about it, they say, well, I've got, this new machine, it's got 10 times as much disk, I'll give it, proportionally 10 times more. But then you start getting into some interesting effects on both failure. You've got, much more of your data is on one particular machine, so the consequence of that machine failing is felt by more nodes in the cluster. And similarly, the amount of workload that it can handle may be slightly different than you expect.
Is this a realistic scenario, or is there where there's like a wide variety of different hardware?
Oh, absolutely. And we had a customer that wanted to retain all of the data that they'd ever written, and they went through, and I think we went through 2 or 3 generations of machines with them, where they went from, I'd say, something like 5 or 6 gig of storage to 24 gig of storage, and then beyond that to a lot more. I may have skipped a generation there, but yeah, absolutely it happens. And for these sorts of operational live databases, it's really important to be able to evolve them and move on. And if you're going to sell a scale-up database, then you do have to be able to truly scale out.
Okay, a Dynamo type of database often sits at the bottom of a call stack for services. So like in Amazon's service-oriented architecture, you'll often have one service calls another, which calls another service, and eventually somebody makes a request to a database. How did this idea of like services calling each other and then databases eventually being at the bottom of the call stack, how did this affect how the Dynamo authors looked at the idea of service level agreements and latency, tail latency?
Yeah, so that's actually I think that's one of the really important contributions to engineers that I speak to, that they now think in terms of high quantile latencies rather than means and median time, mean times for their requests. That they very much understand that if it's going to be a complicated service that may, possibly put it another way, databases deal with a wide variety of information. And if it's something like a user personalization record, we had examples where, for example, a customer had registered several hundred devices, whereas the average customer has 1 or 2 devices registered. And that can make a real difference on the latency. If you just look at means, then it's really hard to tell how much impact those outliers are having, whereas the Dynamo paper talks a lot about how important it is to measure sort of the quantile latencies of your system at the 99th or the 99.9 percentile, so that you can see what the experience is for every customer rather than just for your average non-existent customer, because nobody is the average customer if you add up all of the request times and then divide it by the number of times you made a request.
So is there any way to put a finer point on that and to put it in a different, I worked at Amazon briefly, although it's not like I took any domain knowledge from Amazon and applied it to this. So there's no conflict of interest or anything in this conversation. But, one of the things I think they talked about during orientation was 9.9's availability and blah, blah, blah. And I didn't really get it at the time, because it was just during orientation. I'm like, okay, so why do we need this 99.99? Why is the ninth 9 so much important, or the fifth 9?
The availability time and the quantile. Well, I think it's just about experience, really. If you were going to bring it down to this high level thing, why it matters. I've never actually worked for Amazon, so I don't quite know what they do in their their interview stuff. But if you have a system that responds within a bounded time for 99.9% of the time, you know that all the systems built on it will, if they respond within some bounded time, provide an experience to your customers that is within what they think of as tolerable, without moving off to some other website or presumably the nightmare scenario is that somebody goes to a brick and mortar store and actually buys something. Mm-hmm. So there's that on the latency stats, and on the uptime stats, the 9.9's availability stuff. That's simply about being able, if your business runs on the internet, you need to be able to service things 24 hours a day, and outages really cost you, and it must cost Amazon a tremendous amount of money if they're not able to sell things online.
The other thing I think about is when you have a bunch of services calling each other, and let's say one service has 4 9s of availability, the next one has 5 9s, and the next one has 3 9s or whatever. When you have a top level service that calls a service that calls another one that calls another one, the overall request latency or reliability or whatever you're trying to measure is the product of those different sets of 9s or whatever. So you get this compounding problematic effect. Would you say that's correct?
Oh, absolutely, and okay. You're only as strong as your weakest link, and it drives you nuts on a website if some of the links take a lot longer to load than others and prevent the main content coming. So that's why it's really important to intelligently layer your system to have things in there to, for example, short circuit if you can't display content at a certain time, to display default content, to drop personalization if that's not possible at that time, just so that you keep the experience going. That's a very good point.
Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/SEDaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/SEDaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. Let's talk about the underlying data storage model. You've referred to consistent hashing a few times. I think this is a really important concept. What is consistent hashing?
So consistent hashing is a technique used for distributing data to a number of servers, so that if you change, the membership list of it, the data movement is proportional to the sort of size of the change, rather than re-scrambling everything. To contrast the two approaches, if you had a set of keys of things you wanted to store and you just hashed them and then you took it modulo the number of servers you had, if you change the number of servers, then there's significant data movement around there. Whereas with consistent hashing, you are able to just move a small number of those data items in proportion to what you've changed. So we can talk about the details if that would be useful.
Yes, let's talk about the details.
Sure. So instead of doing the really simple, stupid hash it and stick it in a small number of bins, instead, consistent hashing spreads a number of tokens through what's called the hash ring. So if you imagine taking something like Dynamo uses an MD5, Riak uses a SHA-1 of the key, and if you view that 2 to the 160-bit space as a giant space where you can have tokens in, each of the nodes gets given a number of tokens in the sort of classic consistent hashing distributed throughout that space. And whenever you want to find out where data should go, you simply look for the next token larger than the hash value that you've got and store it on that node. The way that the Dynamo system extends the consistent hashing is you could imagine, instead of just finding the first one token that it finds, it will move on and pick the next n tokens that it will find on unique nodes and use that to actually select which nodes to store the data on. And if you either add new tokens in there or you reassign different nodes to own those tokens, then only the data in that small portion of the hash space is moved rather than everywhere being moved. You can sort of imagine it as a giant never-ending ring that, after 2 to the 160, it wraps around to 0. You could find any point in that ring, treat it as a hoop, snip it with a pair of scissors, hold on to one end, and watch it unroll as a giant list of nodes that you can store data on.
Right. And I mean, well, I think a great, analogy to thinking about this, the ring, it kind of reminds me of just the modulo operator where, as a number, if you go from 0 to 5 and you're modding by 5, and then you go from 5 to 10, it's almost like you're looping around an array again. I mean, this is the classic, hash table 101. Mm-hmm. So as you said, well, let's kind of go through a little more of an example, because I think this consistent hashing is fundamental to highly scalable distributed systems. Dynamo is incrementally scalable. That's another feature that the authors were insistent on talking about. And so a company, like you said, can start with like a small cluster of 5 or 6 machines and gradually scale up as needed. And you already talked about this. I'd kind of like to just run through another example. Like, how does consistent hashing enable this scale up?
Scale up and resilience. So, okay, so if you imagine you had a system with 4 nodes in it to start with, one of the things that's really interesting about the Dynamo paper is if you read it carefully, half of it's written with them using one system for doing their consistent hashing, and then they sort of refine it to solve some operating problems that they had in later parts. So they refer to that in the experience piece. What's probably better to talk about is how they end up doing it rather than the sort of perfect consistent hashing.
Sure.
The way that we actually do it is instead of doing the arbitrary tokens that I was describing earlier, you can more sort of just think of it as a set of pie wedges pre-sliced into a total number of partitions. And you assign those partitions to the particular nodes in the cluster. So it's not quite as flexible as the sort of infinitely scalable. You could have 2 to the 160 nodes with tokens in it, but it is a far more tractable problem and has a lot of nice properties for predictability in that each of the hash pieces will be the same size. So in an example of something like Riak or one of the others that uses the system, you could assign those partitions to nodes. Say you had nodes A, B, C, and D going around the ring. If you were to hash the data so it would, for example, land just before node A, then nodes A, B, and C would be picked to store the data on it. But if, for example, something had happened, there was a network partition or a temporary failure of one of the nodes, A, B, or C, then you could look and you would say, I'm starting at A, B is gone, so I'll fill that in a minute. I have C. So you can go down your list further and say, my next choice would be node D. I'll fill that back in on node B. And so by changing the assignment of where those nodes are, you'll start off with just nodes A, B, and C owning all of the slice those partitions. As you add more nodes in, you can take over subsets of A's, B's, and C's data and put it on node D. Or if you add node E, then you would take another proportion of that, move those partitions over, and it would become responsible for the data. So you incrementally scale out. But in the sort of system B and system C that Amazon describe in their Dynamo paper, the thing that you have to pick early on is the total number of partitions that you're going to break the data into. And so typically you would pick that at sort of 5 to 10 times the ultimate size that you expect your cluster to grow to.
I'd like to go through a couple example types of requests. So if we're writing to Riak or a Dynamo style database, what happens during a write? So we've kind of talked about the consistent hashing level, but if you make a write to this database, what are the different steps that happen, and how does that write get? Well, I guess it will. The write will get hashed to a number of nodes. Whatever the replication factor is. But if you could take me through the anatomy of a write, I'd appreciate that.
Maybe it would be more interesting to do a read, modify, write cycle.
Sure, that'd be great.
Okay, so if you imagine the application is connecting to the cluster of React nodes, the application issues a request to do the read, which we call a get typically because it's sort of key value inspired. Once the node receives it, it could be any node, or the client could be smart enough to understand some of the partitioning to try and avoid some of the network hops. But let's just assume talks to a load balancer, talks to any node. At that point, you simply have a key and a total number of replicas that you need to receive to accept the write. And we typically set that to be a quorum so that we're able to tolerate failure of any one node. So typically you'd be looking to make 3 requests to the other nodes to get the data and request 2 of them to come back. So the consistent hashing algorithm gets applied on the key. We find the preference list, which has the what we call the primary nodes, if everything is happy, and then a list of fallback nodes to go and look for it if the primary nodes are down for you. The system starts up a coordinating FSM, which is what actually runs all of the quorum logic. It will issue a request to each of those nodes, say, please, can I have your local version of key K1, whatever we're doing. Then it waits for replies. Each of the nodes get those requests. They will look in their local key value store, and they'll get both the value that's stored, and alongside that value, we have what's called a version vector, which is what we use to track the causality, which we can talk about a little more in a minute. That data gets returned to the coordinating FSM, and once it has sufficient number of replies, so as soon as the second reply comes in, typically, we'll reply back. Well, we'll take the information that we received from those 2 nodes, we'll compare it to see if it's the same, in which case we just return 1 copy. If one of the nodes is out of date, we'll strip it away and throw away older data, which we can detect with the version vector. Or if the 2 things were written in conflict, then we'll actually return both pieces of information back, along with a causal context that we ask the application to pass back when they do a write to explain what the history of the object is. So once the application looks at it, it may have to deal with multiple copies of it, which we call conflict resolution, but it may just have a simple value that needs to update. Well, whatever it decides to do, it takes the new value that it wants to write alongside the causal context that came from the get, and it passes it back to any node in the cluster again. We go back through the same mechanisms of going through the consistent hash string. We start a slightly different coordinating FSM called the put coordinator this time, which does a couple of things. It makes sure it has a new version vector so that we can always detect that this is a new write that supersedes things that we did some gets on. And then it issues that to each of the nodes. The nodes and waits for their responses. On each of the nodes, we look at the local copy, which could have been modified by somebody else in the meantime, compare the version vector of the local copy and the incoming write. If the new write is a descendant, it supersedes the original one, it's overwritten. Otherwise, the two are merged and left to be picked up as a conflict on the next read. And once the write's complete, we acknowledge back up to the coordinating FSM and then return back to the client, okay or failed. And failed is very interesting in Dynamo systems, and that failed should probably be maybe, because even if one of the data items is written, we'll still return fail. But because of the anti-entropy mechanisms that we'll probably talk about in a minute, you may get a fail immediately and then on a subsequent read actually get the data. So I wish they'd written the messages as okay and maybe, unless they have an absolute definite failure where they know they've never got anything across.
Sure. Okay, so let's get into talking about this anti-entropy methods.
Yeah, so one of the other things about having multiple replicas of things without having a central point of control for it is things can get out of sync either, and there's a large number of ways it can happen, either through concurrent actors, so two application threads updating the same thing at the same time, or it could be something like a software bug. Oops, we messed things up in a certain way. It could be that the actual underlying system was destroyed, it lost its file system, didn't realize, came back up and started servicing requests. So one of the parts that I find makes design so nice and resilient is that there's a couple of different layers of anti-entropy, and one of those is the read repair that you described. The get FSM that I described doesn't immediately return once it's got enough responses to talk back to the client. It actually hangs out a bit longer and waits for any late responses. And using the version vectors that we have, we're able to spot which nodes have out-of-date data or which nodes have data in conflict. Build a complete picture of it and then send it back to all of the nodes so that if you lost any one of them in the future, that they all have the same values back. Now, in Riak, the majority of read repairs are probably caused by consistent actors, but we have some stats in there to check to make sure, oh no, I don't have some fundamental problem with my underlying hardware or storage, that I'm constantly read repairing things. So that's one system, but even longer term, people worry about, for example, data that isn't accessed very frequently. Read repair will only actually take care of things when applications read it. And if you imagine you have something like a photo sharing site where you wrote an image, people look at it heavily for the first 24 hours and then hardly ever look at it again. None of those mechanisms kick in to retrieve it. So Dynamo implements a system of synchronization between replicas to look for those sorts of inconsistencies, and it tries to make tries to reduce the amount of data that has to be exchanged by using a system called Merkle trees, which is quite nicely described in the literature, where you effectively make a tree of hashes and then hash all of the bottom level hashes up to higher and higher levels of it and exchange the two top level hashes. If there's a difference in the two top level hashes, you need to proceed layers and layers down. So if things are up to date and relatively similar, you don't have to exchange too many hashes. But if, for example, a whole section of the tree is lost or the underlying backing store, then we can spot those and put them back together before, eventually a cascade of failures would happen. You lose the first replica, you lose the second replica, and you lose the third replica, and your data would be gone.
So are there other types of problems that can arise in an eventually consistent system that we haven't really touched on?
It is an interesting model. I think that my colleague Russell Brown's actually written a really interesting series of blog posts that we have on the Basho blog, talking about the lessons that we learned in getting the causality and the eventual consistency stuff to work. There are a number of very interesting edge cases like Doomstones, which we fixed in a few releases of Riak ago, where you could end up writing a delete operation to a fallback node and then having it returned and overwriting rewritten data. A lot of the problems that we found were around deletion of data, which they don't talk about very much in the Dynamo paper. In fact, I don't think they mention deletes at all. That's been a huge area of effort for us.
Okay, interesting. So I'm sure we could continue talking on that note for the rest of the interview, but I want to zoom out a little bit. So in terms of the Riak implementation, Basho, the company that implemented Riak, the company you work for, Basho took the Amazon Dynamo paper and implemented it into Riak. Tell me the story behind this.
Sure. But back around the time it published, the engineers that worked at Basho were actually working on a very different services internet business. A large number of the execs and engineers had come from Akamai, so they certainly appreciated the operational concerns that went along with the Dynamo paper, and when they saw it come out, they thought it was a sort of blueprint for the type of database we needed to run the internet business that we were talking about. They worked on that for a while until they decided that the internet business wasn't going to make it, and they did a pivot on taking the internal database technology, which was at the time a slightly more opinionated version of Riak that I think had a JSON database sort of 12 months prior to my joining, and stripped that out and made it sort of a pure KV store, a lot more recognizable as Dynamo, straight Dynamo, and published that. So, from those very early beginnings around the sort of nascent time of the NoSQL systems being available, Bash has taken that and we've added a number of things on top of the Dynamo system. We've taken, we've added multi-cluster replication. We went through and added things like secondary indices, a MapReduce system for sort of finding needles in haystacks, because it turns out people don't just need key value access all the time, through to adding things like full text search by integrating with Solar, and obviously I think one of the very interesting contributions that we've added to Dynamo is adding the CRDT pieces to it.
Okay, well, we should talk more about the CRDT stuff. I'd love to get into that, but sure. I'd also like to know, first, what parts of Riak were difficult to implement, because the Dynamo paper, it's more of like a very loose discussion rather than a in-depth implementation. Were there any parts of Riak that were actually like hard, like really difficult to implement just because the paper didn't describe the recipe in detail?
Oh yeah, and no doubt the version vectors stuff has been a huge learning experience for us. But across releases, that's one part. The section on foreground and background work is only maybe a paragraph long, but those are wise words for anyone ever implementing a system like that. There's a lot of things that happen in the background, like data being transferred, and making sure that doesn't impact your foreground latencies is actually quite a serious design concern. And I think possibly the effect on partitioning and loading of the consistent hashing stuff is possibly a little understated as well. Definitely making sure that clusters are balanced and handling their workload, and the way that the impacts of failures isn't particularly discussed. But it's actually been a great point of learning with our customers over the years to harden Riak up as a true enterprise database.
Were there any places where the original Riak implementation deviated from the Dynamo paper?
Yeah, so I know that the original Riak implementation used sort of client-side vector clocks, which we relied on the clients to keep track of their own actor IDs, which is quite different, which we backed away from and went back to the Dynamo style for Riak 1.0. The original Dynamo, I think, was fixed in the replication factor for the entire cluster, but Riak allows you to do it per bucket, which also caused us a few heartaches on those lessons that I was talking about, partitioning and data, and load on each of the individual nodes. Just trying to think of any others that would be there. Possibly the way that the vnodes are architected is slightly different to the design. I think vnodes are a more logical concept in the Dynamo paper, but in Riak they're sort of fairly functional components as it maps into sort of Erlang programming language rather than it just being a logical mapping.
Okay, so let's get into the discussion of CRDTs like you mentioned. Explain what a CRDT is. So
a CRDT is a convergent or a commutative replicated data type, which is a very nice acronym for describing data structures that you're able to combine easily in an eventually consistent system. So a very good example would be something like a counter. If you had individual nodes that could be isolated and working separately, if you just incremented a counter by reading it, looking at the value and writing it, when you have a conflict, it's really hard to know what the actual count is, right? So let's say one copy says it's 7, one says it's 9. Is it 9? was there a divergence when it was 6 on both of them, and one got added 1-2 and one got added 6-2? So one of the simpler CRDTs that you can think of is a counter, where instead of keeping a single integer, we keep an integer for every actor that can possibly modify it, and they can only ever modify their own. And you get the value of the counter by adding each of the individual pieces up. So I guess that's a long-winded way of saying that CRDTs are a sort of a formalism for handling all of the conflict resolution that's a little bit hand-waved over in the Dynamo paper about how easy it is to make a shopping cart. It gives sort of programmers the primitives that they need, things like sets, maps, counters, and has defined semantics on how they can be updated and come together without having to think about all of the work that you need to do to implement conflict resolution on that accurately.
I noticed you didn't use the acronym conflict-free replicated data type. Is there any reason for your preference of the naming?
No, I've never heard them called conflict-free replicated data types before.
Okay. Interesting. That's what I've heard the acronym I've heard the most, actually. So, really? Okay, interesting. So, I mean, I've been hearing more about CRDTs. Why are they rising in importance?
I think because they allow disconnected updates of data, and the world is increasingly disconnected. If you think we're dealing with things like mobile devices that flap in and out of connectedness, and I think because of their properties of being commutative, in that you can reapply the same operation to them multiple times, it simplifies a lot of design concerns. So when you're dealing with the sort of synchronization and coordination problems, they're a very nice fit for those classes of problems.
Right. Okay. So Riak is by default eventually consistent, as we've discussed in many different paths. So is there a modularity to where a user can enable strong consistency?
So we do have a strong consistency path in Riak that Joe Blomstead wrote based on multipaxos. So and that does have some of the restrictions that some of the sort of more traditional ACID things that Dynamo is trying to move away from. It turns out that there are some class of problems that you need to have some point of record for. For example, if it's allocating a unique user ID or something like that, there's no way around it. And we were trying to find ways of enabling people to use eventually consistent Riak for most of the scalable problems, and then putting some of the smaller things through the strongly consistent path. It's interesting whether or not people want that in Riak or not. And some of the work that we need to do on it isn't totally finished. We don't have it working in the enterprise project for multi-class replication because of all of the synchronization problems that entails. So it's an interesting thing for us to bridge those worlds.
Is there an example you can think of where you would really want strong consistency? Like one of those small bits of the architecture where you'd want strong
sure.
consistency?
I mean, one of the motivating examples was in our S3 clone. I think we call it Riak S2 at the moment. And in that, you need to be able to create a unique bucket name. And for that, we had to write a separate standalone service that ran next to Riak called Stanchion that handles those points of serialization, whereas it would have been ideal to have it as part of the database.
Okay.
And we can get some of those things. One of the things that I didn't really stress earlier was that some of the strangeness that you get with eventually consistent is around sloppy quorums, whereas we allow that fallbacks to be used, but you can actually disable that and restrict your reads and writes to be primaries, which gets you some of those pieces, but it's not the same as full strong consistency.
What is a sloppy quorum?
So a sloppy quorum is where you allow the fallbacks. So if you just have primaries, then you would just call that a quorum. But the extending the preference list into the non-primary nodes when they fail is where it becomes a sloppy quorum. So that's where you get some of the availability characteristics. For example, we had a customer push out a network configuration that completely isolated 60 Riak nodes from one another, but still allowed client traffic. Because Riak allows sloppy quorum by default, each of those nodes spun up 3 replicas of the data of everything that was written to it, And then when the network engineer realized his mistake 2 minutes later and fixed it, they all were able to put that data back together and send it back to the right place. If you hadn't had sloppy quorums enabled, then it would have rejected those writes on a large number of systems. But because it was allowed, then sure enough, it put itself all back together, which I would have liked to see a multi-master MySQL system handle.
So if I'm correct, what you just said was like, so there was a network partition, and so half of the there's a network partition, and the database, the different partitions of the database realized this, so they made replicas within each. They made additional replicas.
Yeah, they started with empty replicas, effectively.
Right. So once that partition was eliminated and they were merged back together, do the additional replicas that were created, did those get eliminated?
Yeah, it all gets merged back. It gets sent back to its proper home. The data gets written on the real node, and next time there's a get, then the node gets a chance to. The client gets a chance to resolve any conflicts that were updated in the meantime.
Very cool. Riak is written mostly in Erlang. Why is Erlang a useful language to write a eventually consistent Dynamo-style database?
Yeah, I mean, quite a few of the clones came out in Erlang. Partly because of the time, I think Erlang was rising in popularity for dealing with these sorts of problems. It has a large number of primitives in it that are very good for building this sort of system. It has a built-in distributed network protocol, so you can just set up a cluster of Erlang nodes. You can send messages to processes between nodes. There are common libraries for building finite state machines. It has its socket handling and network handling is very nice, and it's a very nice. For people who can tolerate Prolog, it has quite a nice layout of how messages are processed and pattern matched. So Andy Gross, who was our chief architect a long time back, wrote a portion of a Dynamo system on the flight cross country just as a proof of concept. And I think that's part of the power of Erlang. For Basho itself, as it was thinking of running a service business, Erlang has a lot of very nice qualities for running a service business, as probably WhatsApp may tell you. There's very nice introspection and tracing features inside the VM itself. It's possible to look at processes sending messages, do things like hot code loading and patching things as you run, which has been invaluable for us during support scenarios. But if you're not used to some of Erlang's warts and how it was built as a telecom management platform, so it's fairly technical. It has philosophies that most other programming languages don't share, like letting it crash, and writing out a big log called crash.log can be a bit scary to customers. So it's taken a while for Basho to learn that where we need to put a nice veneer on it, if that makes sense. So we did a nice project called Cuttlefish to go from the somewhat what other people describe as an arcane syntax for describing data structures to a nice sort of sysctl style system for controlling it. And similarly, we've done work on improving the log system to look a bit more like logs that people expect from normal systems.
Yeah, so we did a show with Joe Armstrong, who created Erlang, and it was pretty interesting. But you mentioned that you kind of worked on kind of a veneer for Erlang. What do you do?
Only as far as the user experience. So, for example, making sure the configuration file isn't in Erlang term format. Instead, it's written as something that somebody would normally just configure a Linux kernel with or something like that. And similarly, it's got an internal error logging system that isn't particularly, doesn't spit things out quite the way that people are used to. So a developer who's consuming the Riak database doesn't need to know anything about Erlang. Yeah, exactly. Yeah, and that's been obviously for people who love the language, like a lot of the people at Basho do, it's a little bit of a mind shift to understand that everyone else hasn't invested the time in understanding what some of these messages mean or why these concepts exist. It's very much an adoption thing. I mean, the people who very early took on to pre 1.0 Riak were interested in things like Erlang and really liked it and didn't care so much, so we sort of ignored it for a while. But as it became adopted by a more mainstream environment, or indeed by people who were asked to run it rather than chose to run it, then you have to do what you can to lower sort of the impedance between their expectations and what they actually receive. Parts of the Riak system are also written in C and C++. What are the parts
that you need for C and C++?
So at the moment, it's mostly the back end. We have our own key value store called Bitcast that Justin Sheehy and Dave Smith wrote back in 2010 when we couldn't find a bounded latency key value store. That uses some C extensions to do key management in memory and indeed issue p-reads, p-writes to the kernel. But since 2011, so we've been investing quite heavily in Google's LevelDB, and that's all written in C++. So you can wrap C libraries up in what's called a NIF, a native interface function, and sort of call it as part of the sort of standard Erlang code. But you do have to be a little bit careful about not messing with Erlang's internal opinions on scheduling.
Yeah. Okay. So I'd like to zoom out a bit since we're kind of running up near the end of time. So the Dynamo paper inspired several other systems, like you've mentioned at the beginning, and let's talk about a few of them. How does Dynamo, or maybe the better question is, how does Riak compare with Cassandra?
So I would say that although they're both inspired by Dynamo, they took a slightly different path. That Cassandra is a hybrid of Bigtable and Dynamo. And they've sort of worried a lot more about, I think, the performance characteristics of it and some of the possibly data layout. Whereas Riak's focused a lot more on the operational concerns, the cluster management, the adding routing nodes, the anti-entropy things inside it. And I think critically for me that the causality tracking is the big difference between Riak and Cassandra. They don't use version vectors like they do in Dynamo and Cassandra, last time I checked. Whereas Riak has the option to use them, or you can revert to a timestamp-based system if you would like to.
Sure. Okay. You also mentioned Voldemort. How does Dynamo compare with Voldemort?
So Voldemort is a very faithful implementation of Dynamo, and in fact, I looked at the sources a lot, both on Riak and the previous Dynamo clone that I worked on, closed source. So, you can see the concept in the Dynamo paper there. If you're not a Java programmer, it's perhaps a little harder to get into, but there's a very interesting corollary between early versions of Riak and comparing the style between the Java and the Erlang version. Voldemort, at least last time I heard, doesn't have any sort of commercial sponsor as part of it, so it's kind of, I suppose, diminished a little bit. I don't know how many people still run it open source or run projects on it, but I guess that's probably the bigger difference there, that Riak is very much an alive and healthy commercial enterprise versus just an open source project, and I think a lot of the LinkedIn people have probably moved on. Yeah.
So I saw a talk that I think, so it was one of your colleagues. I think it was the guy that you just mentioned. Was his name Andy Gross?
Uh-huh.
Yeah. So I saw a talk that he gave, and he said that the authors of the Dynamo paper almost got fired for writing that paper. Do you know if that's actually true?
I have absolutely no idea. I would love to sit down and have a conversation with those guys about it.
Oh, okay.
A great number of implementation details have been very, very good to know a few years ago.
Okay. Well, okay. So on that note, do you have any insight for how closely Riak mimics the Amazon proprietary implementation of DynamoDB?
So as far as I know, DynamoDB is actually quite a different system from the original Dynamo they wrote.
Oh, it's quite different. Okay.
I believe so. There are things that you could implement on top of it, but I think it's a rewrite by a different team in a different place. But again, I don't know that for certain.
Oh, so it's totally unrelated to the Dynamo paper.
As far as I know, but again,
Okay.
I'm by no means an authority on any of that.
Okay. All right. So what is the future of Riak, and what is the future of Basho? What are you guys working on?
So at the moment, we're very interested in continuing to enhance the sort of use cases where it can be used. We continue to innovate and do research on CRDTs and work with a European research group on that called SIG-Free. And we're also very interested in sort of making it easier for people to use the technology by sort of investing in stacks that compose a bunch of the components that our customers frequently use together. And probably our interesting push at the moment that's also worth mentioning is support for time series data. By playing some tricks with the way that we partition the data, we think being able to handle both immutable time series data is something that we can add a lot of value to people who like this sort of scale out system.
Okay, interesting. So what's the relationship between Basho and the open source community?
So we are an open source database. The majority of the product is in open source and available on GitHub for people to inspect, and a number of our customers look at it. A number of customers and open source users really value being able to look at the source. We accept pull requests, etc. We do have enterprise offerings that extend some of the work that we have to be able to do things like multi-cluster that build on top of the product. But we're just a open source database with an enterprise extension. I guess open core is probably the more accurate description of it.
Okay, right. Sure. Well, Jon Meredith, thanks for coming on Software Engineering Daily. This has been super interesting conversation, very helpful to me and my personal understanding of eventual consistency and Dynamo and its impact. So thanks for coming on.
It's been my pleasure, and my apologies to people who couldn't see me waving all these things in the air when I was trying to describe them.
It's always hard to know, what is the level of technical depth you can go into in a podcast, or what are the things that you traditionally need diagrams or a slide share or something to engage, to engage the audience without their eyes glazing over, or their ears glazing over in this case, I guess.
I agree. Well, if they're interested, there's lots of great materials out there on various blogs from Basho to all things distributed to Peter Bayless and stuff. There's a wealth of information. So
definitely, and we will put some of those in the show notes.
Definitely. Cool. Lovely talking to you.